going to begin looking at lab exercise 7, the Earth-Sun relationship, that we're going to be looking at heat energy drives Earth processes that comes from the sun and sunlight. So here's a picture of the Earth shown for size comparison relative to the sun. That we could say that 1.3 million Earths could fit inside the sun, 109 Earths could line up across the sun's equator. The sun's mass is 330,000 times that of the Earth. In gravity, right, F of g equals g, this very, very tiny value, equals 2 masses at a distance squared. That it's a relationship. That gravity is what provides the centripetal force keeping Earth in orbit, as to the sun orbits the Earth. Here we see the Earth-Sun relationship, that the Earth is moving. When we talk about rotation, this is what we're talking about, rotating around this internal axis. This leads to day and night. The side facing the sun is daylight, and away is nighttime. The revolution, this is where the Earth revolves around the sun as its external axis. Because the Earth is an axial tilt of 23.5 degrees, different locations of Earth receive different amounts of direct sunlight. In the picture, you should be able to make sense as to why both tropics have significance, because they're found at 23.5 degrees north and south. So if I look at this picture over here, we're looking at June 21st, our summer solstice in the northern hemisphere. We're observing that the noon sun would be located at 90 degrees or perpendicular to a person standing on the surface. And in the winter solstice, the sun would be directly overhead as well, over the Tropic of Capricorn. So the sun is, as we would view it at the noon, or the noon sun in this case, would be oscillating between the Tropic of Cancer and the Tropic of Capricorn. And these are just the natural rhythms, periodicity of a normal calendar year cycle. And then here obviously we have an equinox, and here we have an equinox too, where the equators, the noon sun would be perpendicular to a person standing on the surface. So now let's get into the Earth's location in space. So the Earth is located on average at 93 million miles, which is 150 million kilometers from the sun. The Earth-Sun distance is referred to as 1 AU, or 1 astronomical unit. This value changes due to Earth's elliptical orbit around it. That here we could see that roughly January 3rd, the Earth is closest, and then around July 3rd, it's furthest. So we call this here perihelion, and we call this side over here aphelion. That seasons are not based upon distance from the sun. Instead, seasons are the result of the directness of sunlight an area receives, and this is also coupled with the axial tilt. So when the northern hemisphere is tilted towards the sun, the northern hemisphere is getting more direct sunlight. So even though it's further away, it's actually getting the most direct sunlight, hence driving the warmer conditions. So energy from the sunlight is not evenly spread over the Earth. One hemisphere is always dark, right, which we call nighttime, receiving no solar radiation at all. On the daylight side, only the point directly under the sun receives the full intensity of the solar radiation. From the equator to the poles, the sun's rays meet at smaller and smaller angles, and the light gets spread over larger and larger surface areas. Those are what we're going to look at in the red lines. So the red lines indicate the different amount of heat density reaching the Earth latitudes. So this picture here is illustrating one of the equinoxes. We see this because the most direct sunlight is associated with hitting the equator. That the heat density here in and around the equator is going to be much greater than as we move poleward, whether we head north or we head south. That the total heat energy that we will measure in watts, or the power, is going to be distributed over a greater surface area. And we could look at that here. So if I compare here the incoming sunlight angle, we're going to be using a term called insolation. That the more direct the sun angle, the more power in watts an area receives per unit area. Unit area will be referring to meters squared. In the picture, closer the sunlight to 90 degrees or directly overhead receives more energy per unit area. And we'll use the measure of watts per meter squared once again. So the insolation here, notice this is not quite perpendicular, but it's close. It's, it's a little bit off. So it's about 17 degrees off of being perpendicular. But notice this amount of sunlight is spread over 1.04 meters squared. Whereas a much greater angle, we are going to be able to see that the lower the angle is going to be spread over about 2.24 meters squared. So this is going to have a much lower heat density, whereas more direct is going to have a greater heat density. And we're really saying that the greater the insolation angle, the greater the heat density. So here we can compare the equator to that of a pole. Notice that the area that's distributing that heat energy, the poles are going to have, on average, a lower heat density than an area like such as the equator. And the equatorial area receives about 2.5 times more energy than the poles. It's just more concentrated, so therefore a greater heat density. And then clearly we have a less density here and much less density at the poles. So our mid-latitudes are going to have kind of this region in between the equator and the poles. So let's look at this in terms of a picture. We associate warm weather to tropical locations, but we were really associating sunlight angle, even though we don't necessarily think of it in those terms. More direct sunlight leads to higher average temperatures, thus warmer. Less direct sunlight leads to more temperate climate, or even colder or polar climate. That the low sun angle of the poles leads to polar regions climatically. We think of sunlight properly, but often miss the key idea. It's a sunlight angle issue. So here's a picture where it's nearly perpendicular, well, it is perpendicular, that this amount has a much greater heat density. Here we'd talk about a mid-latitude region would have that same amount of heat energy spread out over a greater area. And at a greater angle even yet, we would say that it would spread out even more, so a much lower heat density. So we're adding some language here. So if I look at a 40-degree north latitude, we would say, which is close to us, right? We're 42 degrees north. At 40-degree north latitude, we would say that in the summer solstice, the sun is, well, it's not quite directly overhead, but its highest point is actually going to be 73.5 degrees. And I can calculate this using the Analemma chart. So in this case, as I move from June into the fall equinox, the September, I would see that my sun angle actually is decreasing until I reach my winter solstice, where it's going to be much, much lower. It's only 26.5 degrees above the horizon. And then I'm heading back into my spring equinox, and it's rising again, and then it reaches back to our summer solstice. So the sun's position in space can be calculated based on knowing the latitude in which we are working from and the declination, which is where we'll be using the Analemma chart. So what is the noon sun angle? Well, we can calculate it. The noon sun angle is going to be 90 degrees minus the latitude provided plus or minus declination. So there's a couple rules to it. So if I look at this picture here, we would say that we would say very safely that this is the winter solstice, and we would say that this is December 21st. So if I look at my Analemma chart, the Analemma chart allows one to calculate the noon sun angle. You subtract if it's on top of the Analemma chart. This is for northern hemisphere, and add if it's on the bottom. Another way of looking at it is you subtract if it's on the same side and add if it's on the opposite side. So most of our reference frames here in the Chicagoland area from 42 north, if it's on our hemisphere, if the sun is located on our hemisphere, we will subtract at the same, and if it's on the opposite hemisphere, we will add them together. It's seasonal changes in insolation at different latitudes. Any given time, the intensity of insolation is at a maximum at the latitude where the angle of incidence is 90 degrees. The latitude of maximum intensity of insolation shifts in the northern hemisphere with the seasons between 23.5 degrees, right, June 21st, right, the Tropic of Cancer, and to the minimum intensity of December 21st, which is the tropic where it's directly above the Tropic of Capricorn. So we have the lowest intensity, therefore the lowest local sun heat density at the winter solstice, simply because the sun angle is the lowest. So we can do some calculations. So the noon sun angle. So I'll give you a couple practice problems I'll walk you through. 90 degrees minus the latitude plus or minus declination. So what is the zenith? 20 degrees north on March 10th. So I can find this. I can use my chart. You can use yours in the binder. 20 degrees north. 20 degrees north is going to be my value I place in my latitude value. So it's 90 minus, parentheses, 20. And if I look here, I find March 10th. It's on the opposite side. March 10th is somewhere over here, right here. And I can add my value of 4.5 degrees. So if I add, let's see, 20 degrees plus the 4.5 degrees I get from this value here, I could say 20 plus 4.5 is 24.5. 90 minus 24.5 tells me that my sun angle, or my zenith, is going to be 65.5 degrees. And here's my answer key. I just happened to put it upside down. So what is the zenith of 30 degrees south on April 14th? So notice my reference point is in the southern hemisphere. So the same rules apply. Subtract if it's on the same, add if it's on the opposite. So April 14th is going to be up here. So notice it's on the opposite, so I'm going to add it. So I take 90 degrees minus 30 plus, let's see, 9. I got a value of 9 up here. Here we go, of 9. So 30 plus 9 is 39. 90 minus 39 is 51 degrees as my noon sun angle at 30 degrees south on April 14th. I hope that helps.